I think we can get started. Thanks everyone for joining. My name is Shubham, and I'm going to be talking about how we are building cloud native or serverless OpenSearch at Uber. As long as I can figure out how this works. Okay, so a little bit more about me. I lead the search platform team at Uber, and I'm also an OpenSearch technical steering committee member. Before we deep dive into the search use cases at Uber, I want to start with talking about some of the unique challenges that we see. Number one is that we are very locality specific, which means our searches are very locality specific. We also have a lot of data. We have billions of items and billions of road segments to search from. We are also very throughput and latency sensitive. We have very variable intent across different varieties of searches. Some of them are exploratory, some of them are discovery related. We also have very complex ranking. Sometimes the features are encompassing price, speed, reliability, party size, dietary restrictions, and so on. We are serving about 50 billion plus searches every day across 50 plus use cases at Uber. And these 50 plus use cases are powered by about 150 plus clusters at Uber. I'll start deep diving into the search use cases, starting with Uber Eats. I'm sure that you all likely will have already used it. But when you open Uber Eats app, it asks you to set an address where you have to search. Once you set an address, and if it's an apartment, you are asked to pick a pin where you want your delivery or grocery item to get delivered at. Post that, you are opened with a recommended feed that contains stores and items. And if you don't like that selection, then you can search for a specific item or a store. For example, you can search for pizza near Uber Sunnyvale office. Fun fact about this is that all of these use cases are formulated as search problem, and they're powered by the search platform. Similarly, if you go to the flagship Uber app, you can search for an address. Or if you are on the Earner app, you can search for the address where you want to go towards. Both of these use cases are powered by search platform. Now coming to more complex and real-time use cases, for example, rider and driver matching, we get tons of signals. Two primary signals in this case are coming from Earner app, which is the driver location. And then the other signal is the job, essentially if I want to ride or not. The idea behind getting these two signals is to join this, basically figure out what job matches to what driver and at what location. So what we do is that we take these two signals and then put into our search system. And the search system lets us do query, filtering, and ranking. As an example, let's say if you are in San Francisco and you are near the Chase Center, you can write a very rich set of queries like get me earners, get me drivers who are open for getting an Uber XL within 2 miles of that location. You can also write more complex queries like get me food delivery orders that do not have any assigned courier at the moment so that we can find somebody. Moving on to RAG and GenAI style of applications. We are seeing a lot of complaints across our earners where sometimes they cannot go online because their documents are missing, and that requires somebody to help them. And then we also see some consumer-specific complaints like, they shouldn't be charged a fee if the driver is not making progress. Both of these problems were solved by a human about 2 years ago. And then slowly we are advancing into automating these problem solving. And the way we solve these problems is by using approximate nearest neighbor or nearest neighbor style solutions. What we really do is, under the hood, use our previous Q&A corpus and convert them using a fine-tuned large language model into embeddings or vectors. These vectors are high dimensions. And you can think of these vectors as points in high dimensional space. Once you project them into high dimensional space, then the next problem is to figure out, given a query point, which is a vector, figure out what are the nearest neighbor for that specific point. There are a lot of talks about vector search in this conference. I'm not going to go into deep detail about how we are doing it, because there's a lot of overlap. But I'll let you explore those on your own. But this is one of the other problem set that we are solving at Uber. The current search platform is a custom solution built using Apache Lucene. It's a Lambda architecture for ingestion, which means that bulk ingestion is done using Spark, and the streaming ingestion is done via Kafka. The system today provides native support for geosharding. And system also provides interesting index layout and query operators tuned for Uber use cases, and I'll go deep into it as we go in the subsequent slides. I'll start with a case study about Uber Eats, and I'll walk you through how do we solve some of the complex problems that we have. As you know, that Uber Eats has two main entry points, which is feed and search. This is for consumer to discover several inventory types, like restaurant dishes, grocery stores, grocery items, offers, and so on. And the expectation is to be able to serve both within less than 50 milliseconds at P50 and less than 150 milliseconds at P99, with an ingestion throughput of nearly 100,000 documents upsearch per second at peak. I'll talk about how did we solve this problem with the first principles. So imagine that we have 4 documents that are representing stores on Uber Eats. The easier way to build an index is essentially build a 2-dimensional matrix where each cell is either 0 or 1. 1 represents that a specific term is available in a specific document, and 0 represents an absence of it. So for example, doc 1 contains Costco and Sunnyvale. Doc 2 contains Safeway and Sunnyvale, and so on. Similarly, Safeway is present in doc 2. Sunnyvale is present in doc 1, doc 2, doc 3, and so on. But some of you may have guessed that this is highly inefficient data structure because of the sparsity of the data, and it causes poor performance and poor storage requirements. In fact, this problem exacerbates if you have more items. So what we do, we actually use a fairly straightforward data structure called posting list. It's provided by Apache Lucene. And what we do is that essentially we just store the doc IDs corresponding to the terms. The posting list is essentially a data structure that contains a term to a list of doc IDs mapping. But there are 2 challenges that we face at Uber with this data structure. Number 1 is that we have a lot of queries that are encompassing across multiple posting lists, and they go of the order of hundreds or sometimes thousands. And number 2 is that these posting lists are fairly long, which means that if you were to do an exhaustive search across all thousands of posting lists, it takes a lot of time. We can't answer within 150 milliseconds at P99. So we came up with the concept called static rank. Static rank is essentially a way to early terminate early. What this essentially means under the hood is that we order the doc IDs based on certain ranking constraint that we compute offline. You can think of it in the Uber Eats context, popularity. So doc 5, which is chicken nuggets at Costco, is more popular than doc 7. Just an example. This is not how exactly it happens under the hood, but at a high level, that's what it means. There's no personalization. These are static values that are computed offline, and then these posting lists are arranged. So what we do is that, coming back, we have a lot of queries. We have a lot of posting lists to scout for, and we have fairly long posting lists. So we look at all of them, and then early terminate based on how much can we scout within that time frame, and then we return back the matching documents. As some of you have guessed, there's a big problem with sorting this indexes, because they're usually very compute intensive, and I'll talk about how to resolve this. We also use forward index to store the ranking features. This is useful at the time of ranking post-retrieval, so that we can do more dynamic, more slicing and dicing for our users and add personalization. One key feature that we developed because of the unique requirements from Uber Eats is essentially filtering across stores and items. Given that we under the hood use normalized content so that to avoid the ingestion fan out. We came up with an interesting join concept. This is different than the block join that we likely all of us here know of, and I'll talk about in a minute how it is. But we came up with this approach, and it significantly helped across 4 different aspects, and I'll talk about them. The basic idea is essentially to order, store, and items in the index, which is the posting list that I just showed earlier. As an example, imagine that we have 3 stores, Costco, Safeway, Target, and we have items within Costco, within Safeway, within Target. The posting list will look like a store, which is the most popular one, followed by items which are popular within that store, not globally, followed by a different store, Safeway, which is less popular than Costco, and then followed by items which are popular within Safeway, not globally, and so on. And the reason why we do it comes to the next slide. What we do is that we try to navigate these 2 degrees of sorted lookups in locksteps. What I mean by that is, imagine that we are at a specific parent iterator pointer. So imagine that I'm at doc ID 0, which is eligible for that specific query. Then I can go and look at all the matching items within that store first. And rather than exhausting, I can early terminate, making sure that there is enough diversity of content across stores. Right? So we iterate on store, and then iterate on items, then go back to a different store, then iterate on more items, and so on, until either we exhaust the index or we get enough store and enough items. But coming back to what I earlier said, that this compute extensive, because you're sorting the posting list every time an update comes in, which is not ideal. So what we do, the way we solve this problem is we separate out readers and writers. Writers are essentially consuming these updates, flushing the sorted index on disk, and then shipping the index back to readers to read from. So there's a trade-off between freshness and the efficiency that we achieve from this custom join. And it's trivial to understand that this model can be extended to any arbitrary nested joins. Finally, we also built a key feature called concurrent search in our system. The idea is that rather than thinking of a shard as a single file segment, you convert this big file segment into smaller files or other smaller subshards. What we do is that we trade off more performant queries with more compute, with more CPUs. We actually saw some interesting numbers with KNN or ANN style searches, where you can actually tune the K for each subshard while not giving more compute. So it sounds counterintuitive, but this is something that we observed in production. We were able to get better quality vectors with faster speed without any CPU bloating. So coming to the high-level picture of how our architecture looks like, there is a gateway that accepts reads and writes from clients. The writes are sent over to Kafka. We have a service called ingester. It consumes and posts data from Kafka at its own pace, and then creates this sorted index that I spoke about, ships those index onto a remote storage. Think of S3, think of HDFS. And then we have a searcher service, which actually downloads these segments at their own pace periodically and serve the reads that are coming via gateway. We also have an option to bootstrap, to build an offline index via Spark at the time of bootstrapping or at the time of backfilling. This was great until early 2024, but we started seeing 2 big challenges. Number one was we were not able to keep up with the speed of new features requests that were coming from our product teams. And number 2 was there are a lot of systemic improvements that are going on, especially in the space of semantic search, that we were not able to create within this siloed ecosystem. As a result, what we did, we went ahead and embraced the open standards and worked with this vibrant open search community. Consequently, we joined OpenSearch Software Foundation as a founding member in September 2024, which is exactly 1 year ago. We jointly authored OpenSearch 2025 roadmap with a lot of you guys, and started embracing OpenSearch at Uber. This doesn't mean that we don't have OpenSearch clusters running at Uber. It's just that very critical softwares are not yet, use cases are not running on OpenSearch. A lot of tail use cases have started to get onboarded onto OpenSearch. Now coming to the, what do we mean by cloud native at OpenSearch, in OpenSearch? Before I get into some of those details, I want to touch upon cluster manager in OpenSearch. I'm sure a lot of you guys are already familiar with this, but I'll just give a quick primer for context. The idea behind cluster manager in OpenSearch is twofold. Number one is that it performs synchronous updates. It captures metadata across all nodes in a single monolithic blob store, or blob. And number two is that it creates a synchronous RPC calls across all nodes to make sure that the data is consistent, metadata is consistent across all nodes at the same time. There are a lot of problems that we are seeing with the synchronous cluster manager. Number one is that we see reliability risk when the cluster size goes beyond 200 nodes. The reliability risk largely shows in terms of availability drops, and that too quite frequently. We also see frequent shard movements due to temporary network blips. That's primarily because we are running such system across multiple providers. We see a lack of support for rolling upgrades. I'm sure a lot of you guys see the same problem in your own settings. We also see lack of support for heterogeneous sharding. What I mean by that is uneven replicas per shard support is not there. We can't even, and that is because we have a lot of uneven queries across shards because of our location-specific searches that we do. So we want one query to go to one shard or n shards only, rather than scatter gathering across all shards at the same time. So what do we want to do? This is a bit involved picture, but what we're really trying to do are two things. Number one is that we don't want synchronous metadata update across all nodes. We want that to be asynchronous. And number two is that we want to decompose the metadata in a way that the role dictates what they want, rather than every node getting the entire metadata across all clusters. More specifically, what we're trying to do is that we have a controller that is that we call cluster manager, which tails the metadata across all nodes, and then stores that metadata into an etcd store. All the data nodes, or the coordinating nodes, or ingester nodes, now, rather than waiting on the cluster manager to tell them what state do they have, they actually look at the etcd watchers at their own pace. We have started working on it, and what we have done so far is we have actually created a repo for the control plane changes. As we move forward, we are going to be pushing more and more code changes related to that in that repo. It's called cluster etcd. And we have also done data plane changes into the core so that the data nodes don't know that they are being talked through by a remote cluster or a synchronous cluster that exists today. Right? Eventually, what we're trying to do is we're really building OpenSearch serverless or clusterless, as some of my teammates call it. We are on that path right now, and hopefully we'll have a prototype running by end of the year. We're continuing pushing code, so please take a look at it if you're interested in it, and feel free to contribute. There are RFCs, few RFCs that are already open, so welcome any reviews and comments. We are extending this cloud native work to include term-based sharding and also term-based routing. This is different than UID-based sharding and UID-based routing that exists today. We are also going to be working on building batch index for OpenSearch entirely on Spark, so that you don't have to create a cluster or spin up an online cluster just for creating index sometimes. You can just build OpenSearch index on Spark and then ship them to a different cluster. We will be contributing the efficient parent-child join that I spoke about earlier into OpenSearch. We have already committed that code in Lucene. And we also have planned for using GPUs for serving. Right? Thank you. Happy to take any questions, comments. Yeah. Sorry?
Where is your OpenSearch running?
So the question is, where is the OpenSearch running? Right. Yeah. So the question is that where is the OpenSearch instance running? So Uber runs on-prem right now, but we are also in the plan to migrate to OCI cloud. But we're not. We are running open source OpenSearch by ourselves. We're not running a managed service. Yeah, we are running across providers, if you will. So we have some zones in on-prem Uber, and then some zones running on cloud. That's why we see more frequent shard movements because of the network blips. Yeah.
In your clusterless environment, can you talk more about like how the auto-scaling is done for the nodes?
Can you say that again?
In your clusterless environment of yours, can you talk more about like how the auto-scaling of the nodes is done?
Question is that how does auto-scaling work in the current system? So good question. So we have two systems running, right? Like one is OpenSearch, open source OpenSearch, and one is the custom software. We call it Lucene Plus. So what we do is that we have vertical and horizontal scaling running on Lucene Plus. This is provided by Uber's cluster manager, which is different than Kubernetes, but similar in spirit. We run it per shard because we have heterogeneous number of replicas across shards. So, but the load balancer, the horizontal and the vertical scaler takes care of it. OpenSearch, on the other hand, is running vanilla. We just have one fleet of hardware that we hand over to OpenSearch, and the cluster manager does his job to balance across all replicas. Yeah, we want to bring that feature also into OpenSearch so that we can have per shard level scaling, auto scaling, horizontal or vertical, so that you don't have to pay more money if your one shard is hot, which is what the case today is. Actually, good question. So there are 4 ways we made it more efficient. Number one is that what happens is that if you sort the index, what I didn't mention is that and if you follow that 2 lockstep iterator movement, you actually skip a lot of iterator skips. If you do the math, it tries to avoid a lot of skipping because we collocate a lot of city-based store into one location. So not that we just use the L0, L1 cache of CPU, but we also avoid a lot of Lucene skipping. That's number one place where we save majority of the latency cost. We also try to be smart with encodings. So our index size shrinks significantly because we use delta on delta encoding on a sorted array. It tremendously reduces the index and consequently helps with the latency also.
The parent-child relationship was based on data, but also based on the queries. Like this code over here from this store. So is this all like calculated offline based on previous data and then you create these relationships? Or it's very interesting.
Right. So So the data comes from catalog. Catalogs are fixed, right? For example, let's say if you are in a Costco, you know exactly what items that are out there. Similarly, if you are in a Safeway, you know what exactly items are out there. So that is a source for all the parent pointers. If your question is, do we modify it over a period of time when update comes in? Answer is yes, we do that because if let's say a specific item becomes more popular, then of course it moves higher in the rank as opposed to the ones that are not very popular. So over time that ordering changes, but the pointer is a source of truth is from the catalog. Good point. There isn't any specific timeline right now that we can share publicly, but our goal is to be able to have a prototype for that cloud native effort that I spoke about earlier running by early next year. I think post that we'll be able to share it more to the public. Yeah. The question is that how much is the typical size of the document? It varies from different use cases, but talking about specifically Uber Eats, a document, the way we store document is an item or a store. That is fairly small, limited, order of few kilobytes. We also actually store features like I described earlier in a forward index, and that forward index is a little bit bloated, but I mean nothing beyond few kilobytes per document. Actually, that's a great point. So we definitely are using vector search today at Uber. There's one talk today or tomorrow about it. But we are using the vanilla Lucene vector search support today. But we do a lot of creativity around it. Rather than using, for example, rather than using like very high dimensional vectors, we actually use some style of quantization like scalar or product quantization, if you're aware of it. Lucene provides scalar quantization today. And we get great benefit from doing that. We also try to tune the K that I spoke about earlier using the subshards, because when we fan out the scatter gather, when we fan out the request across multiple subshards, we don't have to retrieve all the K items from each subshard. So we actually reduce it significantly smaller, and by virtue of that, we get a lot of parallelism. There was a question actually there.
Have you had the need to scale yourself in terms of having increase your shards without downtime to do things like shard splitting?
A good point. We don't do a lot of shard splitting, but we do see one-off instances, and at the moment, all of that is manual. In other words, we create a separate cluster altogether, and then tee the traffic to that cluster, and then decommission. It's a bit manual, but yeah, we don't do that today. Right, yeah. So the question is that do we use forward index for retrieving? And if so, why we're doing it rather than using posting list? I think great question. So we don't use forward index for retrieval. What we use it for re-ranking the content that we retrieve from retrieval stage. So we use the index to retrieve content and use early termination using the sorting that I mentioned. And then we rank it either using embeddings or using different features. We actually use a lot of logits, logistic regression at Uber, slightly moving away from it to now deep learning models. So we use those features. We use those features in the forward index. Right. Yeah. So the forward index in our case is the stored fields that you know of in OpenSearch. Yeah. I should have clarified. Yeah.
What is the tool you use for schema management? Like you talked about list, so it's like that what's changes between stores and items that you have from possible sequence.
Actually, fantastic question. I think that is one of the things that we want. We have built a schema, very typed and tight schema at Uber. And that schema is well-oiled with the Uber's coding ecosystem. But that is something that we have not yet starting to contribute back into OpenSearch. But we do think that there is a chance that we should look at it and then move that into OpenSearch. I mean, we have dynamic mapping in OpenSearch, but we don't technically use it because dynamic mapping is oftentimes dangerous, and I'm sure many of you have been bitten by it. We have been bitten by it many times, so we are trying to not allow people to use dynamic mapping at Uber. But we have our internal schema, which is like Antler-based. Any other question? Okay, great. Thank you, everyone.